Welcome to the number theory lecture on Diophantine equations. This is the last lesson in my playlist on number theory, or at least for now. If I come up with some other ideas later on, I may add some additional lessons, but for the time being, this is the last lesson in this playlist. So let's go ahead and I'll define what these are on the next slide. Diophantine equations are polynomial equations with integer coefficients for which we seek integer solutions. The name comes from Diophantus of Alexandria, a 3rd century AD Greek mathematician whose book Arithmetica studied such problems systematically, though similar questions appear even earlier. You'll see that in some of the examples. So this is pronounced different ways. I say it Diophantine. I've heard it's pronounced Diophantine or Diophantine. So different ways. This is just the way I've learned to pronounce it. And what I have listed down here is pretty much what I set up here. Polynomials. They're raised to non-negative integer powers. Solutions must be integers. And not all problems have solutions, and it can be difficult to determine whether they do or do not. So let's look at some examples. I have some common examples here on this slide. The ones we'll be looking at are mostly in the first type here, linear Diophantine equations. Excuse me. And they're of the form ax plus by equals c, where a, b, and c are integers. And of course, the solutions are expected to be integers if there is a solution. Solutions exist if and only if AB divides C. AB, the GCD of A and B, divides C. So example, 6x plus 9y equals 12. So the GCD of 6 and 9 is 3, which does divide 12. And in fact, there are infinitely many solutions. And I just gave a couple of examples here. X equals 2, that would give you 12, and y equals 0, so that would be an equation. And you have x equals minus 1, that's minus 6, 2 times 9 is 18, and again you get 12. So that's just two possible solutions. Then you have quadratic examples. So I'm sure you're familiar with the Pythagorean theorem, and we know there's an infinite number of solutions to equations of this form. X squared plus y squared equals z squared. And the classic one, of course, is 3, 4, 5, but there's many other solutions. Then there's Pell's equation, x squared minus d times y squared equals 1 for square-free d. In other words, square-free means that there's no square divisors in d. That has infinitely many solutions in many cases. And then there's the famous one, Fermat's last theorem, which remained unproven for hundreds of years. And this is my comment on the last slide about being very difficult to figure out or prove whether or not you have a solution. So it wasn't until 1994 that Andrew Wiles proved that x to the n plus y to the n equals z to the n has no positive integer solutions for n greater than 2. For n equals 2, we know there's an infinite number. Okay, so these are just some general examples. I have some very specific problems on the next slide, and I'll present those, and then I'll also present solutions to a couple of them. I have 3 specific problems here that date pretty far back, although it is after the time of Diophantus. So the first one is attributed to Alcuin of York, 775 AD. Here's the problem. 100 bushels of grain are distributed to 100 people in 3 groups. We'll call them A, B, and C, such that each person in group A receives 3 bushels, each person in group B receives 2 bushels, and each person in group C receives a half a bushel. how many people are in each group. If we let x, y, and z be the number of people in groups A, B, and C, respectively, then we have x plus y plus z equals 100, right? There's 100 people. And then 3x plus 2y plus a half z has to add up to 100 because we're giving a half a bushel here. Now, I know I said that there were integer coefficients, so obviously we need to do something to this equation to make it a Diophantine equation, which is pretty easy. We could just multiply by 2, and that'll get rid of the fraction here. Then there's another one attributed to Mahavirakarya, 850 AD. Let's read that. So there are 63 baskets of bananas, each with the same number of bananas, and 7 additional bananas. The bananas are distributed among 23 people. How many bananas are there in each basket? If we let x equal the number of bananas in each basket, and y equal the number of bananas distributed to each person, then we have this equation here. So there's 63 baskets times x, the number of bananas, and we were told there's 7 left over, so we have this here. And then it says the bananas are distributed equally among 23 people, so that would be 23 times y. We don't know what the number of people are. Okay, so that's the second one. Then the third one is attributed to Yen Kung, 1372 AD. Given a collection of coins of unknown number, if 77 equal stacks of the coins are made, 27 coins are left over. However, if 78 equal stacks are made, there are no coins left over. How many coins are there? If we let x equal the number of coins in the first type of stack and y equal the number of coins in the second type of stack, then the total number of coins equals this here. So, in other words, we have 77 stacks with each with x coins, and there's 27 left over. And then in the second case, we have 78 stacks, but there's y coins in each one of those. And we're basically told these two numbers on each side of the equation are equal. So it gives us a single Diophantine equation. All right, so we'll look at some methods for solving these, and then we'll look into solutions for the first two, I believe, and then this last one I left as an exercise. I just want to mention another problem to emphasize that even though this type of problem is named after Diophantus, the problem type was known for a long time before. So this example here, the cattle problem of Archimedes goes back to 250 BC, so many hundreds of years before Diophantus. I'm not going to solve this here, I just want to give you the general idea. So the problem was attributed to Archimedes in a letter to Eratosthenes. It asked for the number of cattle in the herds of the sun god, given a set of complex restrictions on the number of bulls and cows of different colors, black, white, dappled, and yellow. And there's two versions of the problem. The first version is even difficult. It's solvable by a system of linear equations. The smallest solution requires a total herd size of roughly 50 million cattle. And then Archimedes added even two more constraints, and this is where it's not linear, as you'll see from the constraints. The sum of the white and black bulls must be a square number, and then the sum of the dappled and yellow bulls must be a triangular number. These numbers are also involved with quadratic. So this more difficult version reduces to a Pell equation, which I mentioned earlier, and you notice the coefficient is huge next to the y squared term. The smallest solution for the total number of cattle is a number with over 200,000 digits, and it was not fully solved until the advent of the computer in 1965. The solution was in 1965. Computers, of course, came a little before that. Okay, so after you listen to the rest of this lesson and you get some ideas about how to go about solving the linear Diophantine equations, you may want to take a look at the more detail on this particular problem. I'll give you the link. It's in a Wikipedia article. Okay, so now let's look at some machinery or theorems that we would use to solve the problems from the previous slide. With some rearrangement and simplification, the previous problems, not on the last slide, but 2 slides before the 3 problems I mentioned, can be reduced to solving an equation of the form ax plus by equals c, where a, b, and c are integers. And of course, the solutions are integers 2, x, and y. So we have this theorem, which I'll go through the proof here. The linear Diophantine equation ax plus by equals c has an integer solution if and only if the GCD of a and b divides c. So it's if and only if. We need to prove it in 2 directions. So we'll go in the forward direction first. Let G be the GCD of a and b. This implies that G divides a and G divides b, or equivalently there exists R and S such that a equals G times R and b equals G times S. Okay, so this is our general assumption. Then if a solution does exist to the problem, so going in the forward direction, say ax sub 0 plus by sub 0 equals c, then we have c equals our solution here, and then I'm just plugging these in for a and b. Put in gr here and gs for b, and then you can factor the g out, and then you basically have c is g times some integer, which implies that the GCD of a and b divides c. So that's forward. Going in the other direction, assume that the GCD of a and b, which we'll call g, divides c, or equivalently, c is a multiple of the GCD, which we can write like this. Then we'll use Bozo's identity to indicate that there's a integers x sub 0 and y sub 0 such that g equals ax sub 0 plus by sub 0. Then we just multiply by t. So t times g is c. Then we multiply t times this here. And we get this here, which implies that ax plus by equals c has a solution. It's tx0, these two multiplied together, and then y equals ty0. Okay, so we've proven that in 2 directions. That'll be useful as we go about solving the previously mentioned problems. We have another result on this slide. If the GCD of a and b is equal to g, then the GCD of a divided by g with the b divided by g is 1. Just take note that a divided by g and b divided by g are both whole numbers, since g being the GCD divides both a and b. By Bozo's identity, we have that there exist integers x and y such that g equals ax plus by, which can be written, shown here. A fundamental property of the GCD states that if there exist integers x and y such that ax plus by equals 1, then the GCD of a and b equals 1. So we can apply that here and get that the GCD of a divided by g with b divided by g is 1. Now the reasoning for this is as follows. Any common divisor d of a and b must divide the linear combination ax plus by for integers ax, b, and y. And since ax plus by equals 1, d must divide 1, and of course if d divides 1 and it's an integer, it must be 1 itself. Once we have a solution to a linear Diophantine equation, we can find an infinite number of other solutions. I have a theorem to that effect here. If x0, y0 is a solution of the Diophantine equation ax plus by equals c, where g is the GCD of a and b, then all their solutions are of this form here. X equals x sub 0 plus bgt, and y equals y sub 0 minus agt. So let's look at a proof. Assume we have another solution, x1, y1. Then both our original solution and our hypothetical other solution both equal c. So we can set these two equal to each other. And then I just brought the x's to one side and factored out the a, and the y terms to the other side and factored out the b. So we have this is our equation 1. Then from the result on the previous slide, we know that a divided by g, taken the GCD was b divided by g, is 1. So let r equal a divided by g, which implies a can be written as gr. And let s equal b divided by g, which implies b can be written as gs. Then we'll substitute this and this into our equation 1, which I'm showing here. And then we can cancel the g on both sides. So we get this here. This is our equation 2, which I've labeled. So r is a factor of this term here. R divides s times y sub 0 minus y sub 1. And we know that the GCD of r and s is 1, right? A over g and b over g that's rs. So this is 1. And then by Euclid's lemma, since the GCD of r and s is 1, that means r has to divide the other term. So we have r divides y sub 0 minus y sub 1. Or equivalently, we can say that there exists an integer t such that y sub 0 minus y sub 1 equals rt. Okay, then we substitute this back into equation 2. And so we get r times x1 minus x0. And then we just have s times rt. We can cancel the r's out and we get this here. So the reason I put these in bold is I'm going to take these onto the other, to the next slide, and I'll rewrite these as y1 in terms of y0 and rt, and x1 in terms of x0 and st. So let's go to the next slide and we'll finish this off. So these come from the equations I had in bold on the last slide, here and here. And then I've just plugged back in, for s, I plugged in b divided by g, and for r, I plugged in a divided by g. So if x1, y1 is a solution other than the given solution, x0, y0, then it must be of the form in this equation here, these two equations here. So we can verify that this is a solution, and we'll do that here. So we, regardless of the value t, the integer t, so we take ax1 plus by1, and we'll put in x1 here, and then we'll substitute in y1 here. And so that we get ax0 plus by0 is here. Then the other term is ab divided by gt and minus ab g times t. So these cancel, you get 0. We know that this is equal to c since we knew this was from the original solution. And so ax1 plus by1 equals c. So we've shown that it is a solution, and we've shown the format that it's given by these two equations here. Let's use some of the theory that we developed to solve some of the problems that we mentioned earlier. We'll first look at the banana problem, which I copied up here. I'll just remind us. So we have 63 baskets of bananas, each with the same number of bananas, and 7 bananas left over. The bananas are distributed equally among 23 people. How many bananas are there in each basket? Let x equal the number of bananas in each basket and y equal the number of bananas distributed to each person. So we have 63 baskets, each with x bananas and 7 left over. And then that needs to equal 23 times y, the number of people, times the number of bananas that are given to each person. I'm going to rewrite this as this here, just taking the 23y here to the left and the 7 to the right. And then we're going to use the extended Euclidean algorithm to find both the GCD of these two numbers and eventually a solution to this equation here. So the way it works is we plug in 1 for x and 0 for y, and we get 63. And so that's an equation. And then we plug in 0 for x and 1 for y, and we get 23, and we get another equation. Then we work with these two equations to get a third equation. We see how many times we could divide 23 into 63 without going over, and that's twice. So we'll take twice row 2 from row 1, which I've noted here, and we get 17. Then minus 2 times 0 plus 1 is 1. Then minus 2 times 1 added to 0 is minus 2. Then we do the same thing with rows 2 and 3. We want to see how many times we could subtract 17 from 23 without going over, and it's just once. So we'll take row 3 from row 2 to get row 4. So we get 6. 1 from 0 is minus 1. A minus and minus 2. Plus 1 is 3. Then to get row 5, we can take twice this from 17, and twice this from here, and twice this from here. We get 5, 3, and minus 8. Eventually we want to get a 1, which when we're right there, this last step, we'll take row 5 from row 4, which I've noted here, and we get 1, minus 3, from 1 is minus 4, and then a minus and minus 8, we get 11. So this is saying that minus 4 plugged in for x and 11 plugged in for y equals 1, which I'm showing here. 63 times minus 4 plus 23 times 11 equals 1. And this also gives us the GCD of 23 and 63. It's just basically multiple applications of the Euclidean algorithm on these two numbers, which we've talked about before. So we have two things from this exercise here. Now we want to get this in this form here, but that's pretty easy. We'll just multiply this by a minus 7, and so this first term becomes 63. Minus 4 times minus 7 is 28. Then we have a minus 23, and then 7 times 11. So these two check out. And then we just have minus 7 times 1, and we get this here. Okay, so we have a solution, an initial solution. X sub 0 equals 28. Y sub 0 equals 77. And then in the theorem we had just gone through, we know we have an infinite number of solutions. It's basically the x part of the solution is 28, our initial x sub 0. Then b, which would be the minus 23, divided by the GCD, which is just 1 in this case. And so we get 28 minus 23t. So for each value of t, we get a different solution. Then we take the initial y 77 minus, and then we have a, in other words, this term here, divided by the GCD, which is 1. And so we get 77 minus 63t. Okay, so if we put in t equals 0, we come back to this one here. If we put in t equals 1, then this gives us 5 and 14. And that turns out to be the smallest positive solution. So if we take 5 bananas in each of the 63 baskets plus 7 more, and each person gets 14 bananas. Okay, so that's the problem didn't ask for the minimum solution. So I guess technically we could say the problem is not completely specified, because we could have gone with 28 and 70, t equals 0, getting the solution of 28 and 77, and that would be a lot larger number of bananas, but it would still work. So if you take larger values of t, bigger than 1, so if we take 2, then you get negative in both cases. So that's not going to work if you take the larger values of t. I guess you could take, I haven't tried this, but I guess you could take t equals minus 1, yeah, and then you would get positive numbers both cases. So you would get even bigger solutions as you take negative values of t. But again, given when this problem was stated so long ago and not having calculators, my guess is it was understood that they were looking for this minimal solution here. Okay, so let's look at one more of our problems and see if we can solve that. I went over the extended Euclidean algorithm a little bit quickly, and I decided as a second thought to maybe go into that a little bit more in detail on this slide before I get to the next problem. So I'm doing that here. It's the same problem, but with just a little bit more explanation. There's two things happening here. First of all, we're finding the GCD of two numbers, and we're also finding a solution to our Diophantine equation. So what I didn't mention on the last slide was the algorithm. We're basically using this identity, which we've seen in my previous lectures multiple times, but we're applying it repeatedly, and to the point where we finally get a GCD of 1 in this case here. Now, the other thing I want to mention is, in the previous theorem in this lesson, we know that the GCD of these two numbers, which I called A and B, that GCD has to divide C, this number here. So if what we come up with at the end here doesn't divide this number, then we know we don't have a solution. And in our case, the GCD was 1, and of course 1 divides any other integer, so we're fine in that respect. So just let's take a look at this side here for a moment. So we started with 63 and 23, and as I was mentioning as we were going through the algorithm on the previous slide, you try to find the largest multiple of 23, such that when you subtract it from 63, you still have a positive integer. So that's what I did here. Using this identity, I let I guess x be 23 and y be 63. So we just took over the x, and then we had y 63 minus 2 times the other number, and then we got 23 and 17. And then we just did that again. We took the smaller number, and then we took the some multiple of the smaller number, subtracted from the bigger number. In this case, we were only able to subtract 1 times 17, and we got this here. And the point is, as you go through this, I won't go through all of them, but as you go through this GCD equals this, and then we bring it down to this line, and this equals this, and you notice we keep bringing down the equality, so this eventually equals this final number here of 1. So all this computation going down here, which I've written out in more detail here, is finding the GCD. And then what we're doing on this side is starting with a valid equation here, 1 times x equals 63. So this is an equation, and this is 2. And then we're just doing row operations that match the operations we're doing to these numbers here and getting the GCD. So that we're, as I say, we're combining things together. So what you end up at the end is actually giving you an equation in terms of x and y, values for x and y, times x times 63 and y times minus 23, that equals 1. And then you can modify it as we did in the previous slide by, in our case, multiplying by minus 7 to get what we needed in terms of the format for this equation here. Okay, so hopefully that helps a little bit in terms of the extended Euclidean algorithm. We have another problem from earlier in the lesson. That was the bushels of grain problem, but it wasn't quite in the form of a Diophantine equation, but we can get it in that form. So let's review the problem again. 100 bushels of grain are distributed to 100 people in 3 groups, A, B, and C, such that each person in group A receives 3 bushels, each person in group B receives 2 bushels, and each person in group C receives a half a bushel. How many people are in each group? If we let x plus y plus z be the number of people in groups A, B, and C respectively, then we have the sum x plus y plus z equals 100, and we also have this equation here from the distribution, 3 bushels times each person in group A, 2 bushels times the number of people in group B, and then a half a bushel times the number of people in group C, and that has to also equal the 100, right? There's 100 bushels of grain. We're told that at the beginning. Okay, so we can rewrite this equation here, just taking the x and y to the right. We have this, and then we can substitute this expression for z into this second equation. We get this here. Then you only have x and y and no z term, so you basically get, it's a little bit of work, which I didn't show you here, but if you simplify this, you're going to get 5x plus 3y equals 100. And from here, we could use the mechanism, the extended Euclidean algorithm, to find the GCD of 5 and 3, which we could see is 1 right off. And we would also find an initial solution. You can do that if you like, but it's a bit easier just to guess by examining this here. And you can see that if x is 5, you get 25 here, and then 3 times 25, if we let y equal 25, 3 times that is 75, and you get 100. And that would imply that z equals 100 minus 30, so that would be 70. And no other solutions meet the additional requirement of x plus y plus z equals 100. So that's our solution there. So that was a little bit tricky because we had 2 equations. We needed to simplify one into the 2 of them together to get one Diophantine equation. In this case, we were able to guess at the answer. So the last one I'll leave as an exercise, the one from Yen Kung. But I'll give you the answer so you can check it once you solve it. It's x equals 27 minus 78t, and y equals 27 minus 77t. And the minimum positive solution occurs if you take t equals 0, and you get x equals y equals 27. Okay, and if you want to do this, I would recommend using the extended Euclidean algorithm, and that'll give you the GCD of the 2 numbers in the Diophantine equation, and it also gives you an initial solution. And then our theorem from a couple of slides back gives you the formula for the infinite number of solutions, which I've shown here. And then it's just a matter of trying different values of t to see which one gives you the minimum positive value. And this is the solution. We have one more problem in this lesson. Find the first integer value for n such that f of n equals n squared plus n plus 1 is composite number. Do the same for h of n equals 36n squared minus 810n plus 2753. And I'm also going to prove something. The reason I'm putting this here is you get a lot of prime solutions first. So you may think there's some equation that generates just prime numbers, but in fact, it can be proven there is no non-constant polynomial function f of n with integer coefficients that produces only prime number values for all integer values of n. I'll prove that after I give you the solution to these two. I'll prove that towards the end of this lesson. So let's look at the first one, the f of n equals n squared plus n plus 1. And we want to find the first value of n greater than or equal to 1, such that we get a composite number. And the answer is 4, and I'll show you that here. And then we have the second problem I'll get to in a minute. So let's look at this equation. Here we put in 1, we get 3, 2, we get 7, 3, we get 13, so it looks kind of good. We got 3 in a row. But then when you put in 4, you get 21, so that's composite, 3 times 7. So that's the answer there is 4. Then let's look at the second. The second one's harder because we have these bigger numbers to work with here. So I'll kind of just summarize the value. But you put in 1 and you get 1979. So just to check this is prime, there's some work. Of course, you could go to I'm sure there's an online app that'll check that for you. And then there's put in 2. And you get a prime. For values n equal 3 and 4, you also get a prime. Values for n equals 5 to 18, you get negative. So we were asked for when do we get the first positive composite. I mean, I guess we could stop here at 5, but what's kind of interesting is that from 19 to 44, you get all prime numbers again. So this is pretty good. This is generating a lot of prime numbers. And then if you do 45, and I'm just showing the computations here, you don't need to study these, but the final number that you get when you plug in 45 is 39,203, but you can write that as 197 times 199. So that's the first positive composite number you get out of the equation, but you kind of stop generating primes at n equals 5. It's just that you're getting negative numbers. Okay, so no matter what you do, if you have integer coefficients on a polynomial, you're never going to be able to generate only primes. And I'll prove that on the next. It's not all that hard to prove, actually. It's just one slide to prove that this is impossible. I want to prove the theorem I mentioned in conjunction with the last problem that we worked on. We'll do it by contradiction. Assume there exists a non-constant polynomial f of n with integer coefficients such that for every integer n, f of n is a prime number. Let k be an arbitrary integer. Let p be the prime number generated at k. In other words, f of k equals p. And then consider k plus mp, where m is an integer. There's a key property of polynomials, which I'll prove on the next slide, but just take it as a given for now, that a minus b divides f of a minus f of b. Applying this here, we have taking a to be k plus mp and b equal to k, we have this. And then we just take, going from here to here, we just take the difference, we get MP. Then I'm just plugging in P for f of k. Then this implies that f of k plus mp minus p equals mp times some integer t. Then we can just bring the p to the right, then factor it out, and this implies that f of k plus mp is congruent to 0 mod p. All right, this is all leading us to a contradiction. The congruence above tells us that for any integer m, the value f of k plus mp is divisible by p. However, by our initial assumption, f evaluated at any integer, let alone k plus mp, must be a prime number. The only prime number divisible by p is p itself, or minus p, but we normally don't think of prime numbers as being negative. Therefore, for f of k plus mp to be prime, it must be true that it equals p for all integers m, right? This m was any integer we want to pick here. This means the polynomial f of n takes the value p infinitely many times at k plus p, at k plus 2p, and so on. However, a non-constant polynomial of degree d can only can take on any specific value at most d times. Since f of n takes the same value infinitely many times, it must be a constant polynomial. This contradicts the assumption that f of n is non-constant. Therefore, no such non-constant polynomial exists. Okay, so there's no non-constant polynomial that just puts out prime numbers. Now, not every prime number, but just prime numbers in general. So even that's not possible. So let me prove this result here on the next slide. On this slide, I prove the result I mentioned on the previous slide. Let f of x be a polynomial with integer coefficients. For any distinct integers a and b, a minus b divides f of a minus f of b. So let's prove that. Let f of x be a polynomial of degree m with integer coefficients. So we'll write it out like this, or as the in a summation form here. Then we can write f of a minus f of b like this. We're just plugging in a for x here, or actually in here, and then b. And then we can write this like this here. But then we have this formula. Again, you can check this. I've shown formulas like this a few times in my lessons on number theory. But if you just multiply the a times this and the minus b times this, then everything cancels except for the a to the k and the minus b to the k. So this is an identity. And since a minus b is a factor of a to the k minus b to the k, just from this here, we can pull it out from the summation and let capital Q sub k be the integer such that a to the k minus b to the k equals a minus b times q sub k. In other words, q sub k is this part here. Then substituting this back into our equation, we have this, just taking the substitution here. We factor out the a minus b since it doesn't involve the summation index. Since c sub k and capital Q sub k are integers, the summation, this thing here, is an integer, and then you just have an integer times a minus b equals f of a minus f of b, which means that f of a minus f of b is divisible by a minus b. So far, we've proven one theorem related to functions generating primes. And that's this one here, what I've listed down the bottom. There is no non-constant polynomial f of n with integer coefficients that produces only prime number values for each integer value n. However, there's other cases that we can look at, and I want to kind of give you a summary of those on the next few slides. The first case is where we look at linear polynomials with integer coefficients, and there's a result proven way back in 1837. It's called the Dirichlet's theorem on arithmetic progressions, and it states that for any polynomial of the form f of n equals an plus b, where a and b are relatively prime, so their greatest common divisor is 1, the polynomial will generate an infinite number of primes as n goes to infinity. So not every prime, but an infinite number. And I have one example here. If you take f of n equals 4n plus 3, 4 and 3 are relatively prime. And you can see here as you plug in just a few. For 1, you get a prime. Plug in 2, you get 11. That's prime. 3 is composite. 15 is composite. Then you get another prime. And so what was proven is that the sequence contains infinitely many primes, but not every prime. You can see here we missed 3 and 5 and 13 and 17. So it's missing some primes, but the proof of the Dirichlet's theorem is that it'll generate an infinite number of primes within the set of primes. Okay, so I have a few more results in the next few slides. So we have some conjectures, I guess, they haven't been proven, for polynomials of degree greater than or equal to 2 of a single variable. And as I say, these are unproven. So ideally, we would like to say that a simple quadratic like n squared plus 1 generates infinitely many primes, even if it's not every prime, but at least infinitely many of them. However, no polynomial of degree 2 or higher in one variable has ever been proven to generate infinitely many primes. It doesn't mean it hasn't been disproven either, but we haven't found such a polynomial. So there's the Landau conjecture. It's a famous open problem, one of Landau's 4 problems. Actually, I'll give you a reference to this later, to prove that what I just said here, n squared plus 1 generates infinitely many primes. So this is a conjecture. And then there's the Bunyakovsky conjecture. This is a broad hypothesis suggesting that any irreducible polynomial with integer coefficients, in other words, can't be factored into smaller polynomials, with integer coefficients that does not have a fixed divisor, a number that divides all values of f of n, will generate infinitely many primes. While widely believed to be true, it remains unproven. So this is similar to the problem we had looked at just a little while ago, where we had a 1 here instead of a 41. But this is a famous almost case. This polynomial is famous because it generates prime numbers for every integer from 0 to 39. But however, if you put in 40, you get 412, which is composite. So it is believed to generate infinitely many primes, but so far this is unproven. That would fall into the case of polynomials greater than or equal to 2. So we still haven't found an answer to this. If you want to become famous, you could try proving one of these conjectures. I'm sure it's not easy because these have been around for a bit and no one has solved the problem. Okay, the next slide I'll talk about where you have multiple variables and whether or not those type of polynomials can generate an infinite number of primes. In the case of polynomials with multiple variables, we do have a solution. It's something that was proved more recently. So the idea is you can have variables A, B, C, and so on, and that will generate not just an infinite number of primes, but actually all the prime numbers. And that's something I'll mention in a second. There was some famous work that relates to this. It doesn't actually give you the polynomial, but it's related to this, and I'll mention it here. Based on work related to Hilbert's 10th problem. David Hilbert was a famous mathematician who had posed a set of problems that challenged mathematicians, and some of them went unsolved for a very long time. And so this particular problem that I'm mentioning here is related to the 10th problem from Hilbert. And there's this MRDP theorem from these four mathematicians. It was proved that the set of prime numbers is what's called a Diophantine set. Calling the primes a Diophantine set is a fancy way of saying prime numbers, despite their complexity, can be completely defined by a single polynomial equation using only addition, subtraction, and multiplication. So that kind of led to this result here. In 1976, Jones, Sato, Wada, and Wiens explicitly constructed a polynomial of degree 25 with 26 variables using letters A to Z, so every letter in the alphabet. The set of positive values taken by this polynomial as the variables range over the non-negative integers is exactly the set of prime numbers. So that's pretty amazing. Now, the downside to this is that the polynomial is inefficient. It takes on negative composite values most of the time. However, whenever it outputs a positive number, that number is guaranteed to be prime, and it will eventually output every prime number. Okay, so that's my summary of functions and their ability to generate prime numbers, or an infinite number of primes, or all primes. I have a few references on the next slide, and then I'll conclude this lesson. I'll put these references in the information to the video so you can click on them. You don't need to copy these down, but I just want to mention, I talked about the extended Euclidean algorithm. So there's a nice Wikipedia article that gives an example of that. Then the Dirichlet, Landau, and Bunyakovsky problems. There's also Wikipedia articles on those. And then the last thing we just talked about was the multiple variables. There's a Wolfram article, prime generating polynomial, and I'll give you that reference too. Okay, so that was the last slide in this lesson, and at least for the time being, this is the last lesson in my number theory playlist. If you like this, please give it a like, thumbs up, and stay tuned for my other videos on other topics. And if I think of anything else on the topic of number theory, I'll just add to this. But for the time being, I don't have any plans to add to this playlist.